This video is for Math 1325. We are moving on to Chapter 4, Section 4.1, and this is about techniques for finding derivatives more easily than the long process of doing the limit as h approaches 0 of f of x plus h minus f of x all over h. So we're going to start off with polynomials. Y equals x to the third minus 8x squared plus 21x plus 6. After doing enough derivatives of problems like we did in chapter 3, somebody started to notice that a certain pattern was occurring, and it creates a very nice shortcut for doing a derivative. X to the third minus 8x squared plus 21x plus 6. So we could easily do this with the limit idea. It just would take a long time, probably like 10 minutes for one problem. But okay, so the derivative, we can write this a number of ways. If there's a y right here, then they are usually going to write y prime. That's the symbol for derivative. But it does have other versions. If the original function is called f of x, which is the same thing as y, then they can write f prime of x. So the little apostrophe means you're doing a derivative. You'll even see dy over dx, which is the derivative of y with respect to x. Okay, so the shortcut here is simple enough that even young kids could probably do it. They wouldn't understand what it's used for, but it turns out all you do is multiply the constant in front by the exponent. 1 times 3 is 3. The x stays the same, and then you decrease the exponent by 1. 3 minus 1 is 2. So if you just did the limit as h approaches 0, if your whole function was x to the third and not those other terms, and you did f of x plus h minus f of x over h and simplified the whole thing down in about 5-10 minutes, it would turn out the answer would be 3x squared. 3 times 1 is 3, and the exponent decreases by 1. Somebody did enough of these, they noticed, hey, the exponent always seems to be 1 less than the original. And then they said, wait a minute, this exponent times the number in front always is the constant in front here. So it was just noticing that after you did a bunch of problems. That's where the shortcut was born from. And doing just one term like this, if I just worry about this one term, that's called the power rule. Because I did a derivative of a power, 1x to the third power rule. For polynomials, you just go term by term and do each term with the power rule. Now, they will specify this as a separate rule, the adding and subtracting rule, but really I just think of it as doing the power rule 4 times. So now I'm ready to do the next term. So you just grab the exponent 2, multiply it to the constant in front. 2 times negative 8 is negative 16. And then you decrease the exponent by 1, which makes it a 1, or you can leave it blank. And then this is a shortcut you're going to get used to, but here's what's technically happening. There's even a shortcut inside the shortcut. You're technically doing 1 times 21, which is 21. And then you're decreasing the exponent by 1. The 1 becomes a 0. But x to the 0 is equal to 1, and 1 times anything is the anything. So anytime you have a linear term, 21x is linear, the derivative of it is just the 21. This part goes away because 21 times 1 is 21. So linear terms, it's just whatever the constant is. And likewise, it turns out the derivative of a constant is 0. so that you can just skip that one unless there's nothing else there, because you could literally put an x to the 0 attached to it, because that would be 6 times 1 by doing that. And then you would get 0 times 6 is 0, x to the technically -1, but it won't matter because 0 times anything is 0. So constants, the derivatives are 0, and you won't see them in most answers because there's usually other stuff. Linears, you just get the constant that's in front. So the derivative of this function is 3x squared minus 16x plus 21. We started with a cubic function, and the derivative decreased to a quadratic. That's always going to happen with polynomials. So notice they wrote, for the answer, they wrote one of the versions of it, they put dy over dx. That tells you they want you to do the derivative. Find the derivative, the directions say. So 3x squared minus 16x plus 21. Okay, similar deal. So now you're going to get some other variations coming up. Number 2, y equals x cubed minus x squared over 28, or you could rewrite that, I would rewrite that as 1/28 x squared. X over something is the same thing as 1 over the number times x. X over 3 is the same thing as 1/3 x. So that's why it's better to write it that way, because then you'll see better where the constant is and what the exponent is. Plus 16x plus 9. So we're really doing the power rule and the addition and subtraction rule, but I would just say I'm doing the power rule 4 times. So whether we write dy over dx or f prime of x or y prime, all three of these things really mean the same thing. It usually just depends on the scenario or how the original, usually it depends how this is written. If you have an f of x here, then they almost always put f prime of x. If you have a y, then this or this is acceptable, but they're really all equivalent. So x to the third, that one, we did that one a second ago, that's 3x squared, because you're really doing 3 times 1. And then you're decreasing the exponent by 1 to a 2. So now you're doing 2 times negative 1/28, which is negative 2 over 28, but that would reduce to negative 1/14. And then the 2 decreases by 1 to a 1. Here's a linear term, so the derivative of a linear term is just its constant in front, 16. The derivative of a constant is nothing, so we don't have to put it in the answer. Here's the whole answer right here. The derivative is 3x squared minus 1/14 x plus 16. Notice I did it in about, I could do it in 30 seconds or less if I wasn't explaining it to you. And instead of taking 5 to 10 minutes to do the limit as h approaches 0 idea. But at least you learned why that works. That limit idea really shows you why it works, and then now you just discovered a shortcut that speeds the process up. 3x squared minus 1/14 x plus 16. Okay, now we can get a little bit of a snafu going on. If you see radicals in the problem, or negative exponents, then that can make a situation where you want it in a certain style before you go about doing the derivative. So I have 10 square root of x plus 3x to the 2/7 power. So fractional exponents are really not an issue. If you get x's in denominators, you're going to want to employ negative exponents to bring them up to the top. And then radicals can be turned into fractional exponents. So the square root of x, you should have learned in algebra that that's the same thing as 1/2 for an exponent. A 1/2 power is the same thing as a square root. So they just wanted to see, did you remember that from algebra, that the square root of x is the same thing as x to the 1/2? Because without knowing that, you're not going to be able to finish this. You need to have an exponent 1/2 times the constant in front for the derivative, y prime or dy over dx. So 1/2 times 10 is 5x. Now you're decreasing the exponent by 1. So you're probably not used to this yet. Let me put it here. 1/2 minus 1 is what I'm literally doing. You need to change the 1 so it has this 2 in its denominator. So 1 can be anything divided by itself, so I would make it 2 divided by 2. That way it matches with 1 divided by 2. 1 divided by 2 minus 2 divided by 2 is negative 1 divided by 2. If you have a half and you take 1 away, you end up at negative a half. And then this can sometimes come out okay, but here nothing really happens. 3 times 2/7 is literally 6/7, because you can just do the 3 times 2 only. And then I got to decrease that by 1, so 2/7 minus 1. Make that 2/7 minus 7/7. That way the 1's turning into 7 over 7. That would be negative 5 over 7. Okay, so back in the day when we used to do problems out of actual textbooks, teachers would tell students, do the odd problems, and then you can look up the answers in the back of the book. It turns out there's different ways you could write this final answer, and it may or may not be listed this way in the back of the book was always the issue, even though that's a possible equivalent answer. Another thing is that it's been ingrained in a lot of students since high school that you never leave negative exponents in answers. And sometimes even here in calculus, they will say in a given problem to not do that. But often the directions are very general. Like here, it just says find the derivative. It doesn't say anything about what kind of answers they want. So then actually negative exponents are not bad at all. I could just leave this answer like this. It's going to count it right. Somebody could say, well, I learned in algebra that never leave a negative exponent, so I'm going to put that x to the negative 1/2 in the denominator, and that'll turn it into a positive 1/2. You can do that. It's not wrong. And same thing with the 6/7. 6/7. Put this x to the negative 5/5 in the bottom. Then it's positive 5/5. So this is an equivalent other answer that's either one. Neither one's necessarily better than the other one. Also, sort of an unwritten rule is sometimes you try to put the answer back the way it looked originally. So remember in the original problem how there was a square root here, but a fractional exponent there? So you could change this x to the 1/2 back to a radical. That is equivalent. You could even turn this to a radical, but it wasn't originally, so probably you wouldn't want to, but you could. So here's another third possible answer. And sometimes the back of the book, when we used to do it that way, it wasn't even consistent. One problem they would leave it x to the 1/2. The next problem they would actually change it to square root of x. There was no like consistent way they always did it. And maybe they did that on purpose to show you that it really didn't matter which way you put it. But the problem was students would get one version, they'd look it up in the back of the book and see the other one, and maybe they thought it was equivalent, but they weren't always positive. Did they do it right or not? But the good news here in my math lab is they take any of these possible answers. You can do any of those things. And therefore, why not just stop at the first thing you get? If they're going to take that answer, why waste time doing these other things and or taking a chance you might make a tiny brain cramp of some kind, which could happen to anybody. So I would just leave it 5x to the negative 1/2 plus 6/7 x to the negative 5/2. 6/7 x to the negative 5/7. So they take that version of it. But they would have taken even the other two that I did, or any kind of combination. Like you could do this first fraction with this second one if you wanted to. So there's like more than a handful of different ways you could do that. You could have this version with this if you wanted to. You could do this one with this one if you wanted. There's so many different ways you could mix these three up. So there's probably about 10 versions that they would take here, just depending how you want to write it, because they're all equivalent to each other. So one kind of good piece of news is that negative exponents don't bother us that much in calculus, actually. There's a few cases where they kind of avoid them, but for the most part, it really doesn't matter if you leave your answer with a negative exponent. In fact, sometimes we create negative exponents on purpose just to make things easier, which is about to happen right here, actually. So number 4, you're going to see in a future section a way to do this the way it looks. Although even then, I would not do it that way for this particular problem. 3 over x to the 5th minus 4 over x. You don't know how to do division problems yet. That's coming up in the next section or two. And so we need to change this before. I'm not even doing the derivative yet. I'm still on regular y right here. I would change this to 3x to the negative 5, even though we normally don't do that in algebra. Here it's actually needed. Minus 4x to the negative 1. Once you're in this format, now it's much easier to do the power rule. So the derivative would be, now I have a constant times an exponent, which we didn't have a second ago. 3 times negative 5 is negative 15. And then decrease the exponent by 1, and it's negative 5 minus 1, which is actually negative 6. It's easy to mess that up and say negative 4, but you're decreasing the exponent by 1. Negative 4 times negative 1 is positive 4. Decrease this by 1. Negative 1 minus 1 is negative 2. So this is fine for the answer. Or you can make it look like it did originally if you like that better, and put the x to the 6 in the bottom, and that turns it into a positive. And then same thing, 4, you could put this over x squared if you wanted to. Now here you couldn't put radicals in the answer, but you could do that if you wanted to. So this one really only has 2 different ways to write the final answer, but they would take either one of these two, whatever you like better. But I would just leave it the first time I get an answer that's acceptable. I would leave it that way, because why waste time even doing other things that you don't have to do, and or having some kind of brain cramp or typo and messing it up. Okay, I guess this isn't really different other than we have negative fractional exponents given, but the process is the same. So find the derivative. Notice they have p of x, and then they wrote in the answer p prime of x. See, when it's p of x or f of x, then this is more common a way of putting the symbol for the derivative. So p of x is negative 15 x to the negative 1/5. And then plus 24 x to the negative 5/6. So p prime of x, that's why you read that out loud too, I should mention that. P prime, that little apostrophe is red, prime. P prime of x is a way to read that out loud. Or you just say, for this one, you just say y prime. And this, you just say dy over dx, just like it looks. Dy over dx. Which really means the derivative of y with respect to x is the official way to say it. P prime of x. So I'm going to do the constant times the exponent. Sometimes it works out nice, sometimes it doesn't. This one does, because negative 15 times negative 1 is positive 15, and then divided by 5. That comes out to exactly 3, positive 3 even. And then I need to decrease that exponent by 1. So whatever the denominator is right here, that's what you should change the 1 to be, 5 over 5. It's always nice to work with ones because you just, whatever the bottom needs to be, that's what you make the top. Negative 1/5 minus 5/5 is negative 6/5. And again, we don't care if it's messy as long as it's fully simplified. And then positive 24 times negative 5/6. You could either do 24 times negative 5 and then divide by 6. Or you can divide first and do 24 divided by 6 is 4. 4 times negative 5 is negative 20. It works either way. 24 times negative 5. I have hit this negative button on this calculator. 24 times negative 5 divided by 6 is negative 20. Or if I would have done 24 divided by 6 and then times negative 5, notice that's also negative 20. So if it's all multiplication and division, you can do it in any order you want. When there's addition and subtraction mixed in, then it's not quite that easy. So I need to decrease this exponent by 1, negative 5/6 minus 1, make it negative 5/6 minus 6 over 6. So you got those matching denominators, negative 11 over 6. And yes, you could change the negative exponents back to positive, or not even back to positive. You could change them to positive. So you could have 3 over x to the positive 6/5 minus 20 over x to the 11/6 if you wanted to. But I'll just leave it this way and save time and effort. 3x to the negative 6/5 and minus 20x to the negative 11/6. Oh, I said negative 20, but I typed positive. That's weird. Minus 20. Okay. See, there's a slight typo on my part. If I was taking a test, I would have lost credit for that problem, even though I said it right and my work was right. I had minus 20 here. I even said minus 20, but I typed a positive 20. It's always possible. Everybody's going to have brain cramp mistakes all the time. So that's why I don't waste time doing other versions that are equivalent, because you can just have a slight brain cramp at any point. Okay, dy over dx. Now, again, you don't know how to do division yet. So there is another way to do this as a division problem that you're going to learn maybe in the next section, actually. But even then, this problem doesn't have to be done that way, even if you get this, and you won't get this in the next section. But if somehow later on they threw one at you like this, the better choice is what I'm about to do here. But when you get to the next section, you won't have this better choice to make, actually. What makes things easier here that won't happen later is that the denominator has one term only. In the next section, the denominator will have more than one term, and then we won't be able to do this shortcut. But whenever there's just one denominator term, then you can divide each numerator term by that. So this is a simplification I would do just to make the problem a lot easier. X to the 6th divided by x to the 2nd is x to the 4th. And 4 over x squared, that doesn't simplify, but I could rewrite it as 4x to the negative 2. You always want polynomial format, where you have a constant, a variable, and an exponent. It's okay to write 4 over x squared. It is equivalent to that, but you don't want a division problem if you can avoid it. You don't know how to do division problems yet anyway, and even when you learn it, it's a lot longer than this, so I would do this. So now we're ready for dy over dx, the derivative of y with respect to x. So it's 4 times 1 is 4. Decrease the exponent by 1, third power. Positive 4 times negative 2 is negative 8. X to the negative 2 minus 1 is negative 3. So this is perfectly fine for the answer. 4x to the third minus 8x to the negative third. 4x to the third minus 8x to the negative 3. So see how quick that went? When we learn the division process next time, you'll see it's a lot longer. So you could actually do this. Once you learn the next section, you could come back to this problem and do it that way if you want. It's just going to take a lot longer. Okay, so find the slope and the equation of the tangent line. Remember, tangent line is what derivatives are about. Slope of a tangent line is literally derivative. That's what you want to remember. Anytime you hear the phrase slope of a tangent line, that's calculus code for derivative. This is a derivative. So they'll say that to see if you know, oh, I'm supposed to do the derivative at this point. Find the slope of the tangent line. That's the same thing as they just said, find the derivative. So I'm first going to take the equation and do the derivative of that. That's pretty easy. And then they want me to get the equation of it too. That's the other extra thing, but that extra thing is all algebra actually. Getting the equation of a tangent line has nothing to do with calculus. It's algebra. So y equals x to the fourth minus 18x squared plus 81. And then they give me an exact x value to go to, but that'll be when I'm trying to get the equation of the line. First, I want to find the slope of the tangent line. So that's the derivative, y prime or dy over dx. So 4 times 1 is 4. X to the third. 2 times negative 18 is negative 36. X to the 2 minus 1 is 1. And the derivative of a constant is nothing. So here's the derivative, which is how I can find the slope of a tangent line. Because remember, the slopes of tangent line, they can be different at every different x you go to if the graph is curved. So they want me to go to exactly x equals negative 2. So this is a reason for writing f prime of x. If we had written f prime of x for this answer instead of y prime, then it's easy to say, okay, I'm doing f prime of negative 2, or especially when you have to plug in more than one of them. So plug negative 2 into the derivative function everywhere there's an x, and just do algebra to calculate the answer, order of operations. Negative 2 cubed is negative 8. Negative 8 times 4 is negative 32. Negative 36 times negative 2 is positive 72. Plus negative 32 is 40. So by plugging negative 2 into the derivative function, that tells me the slope of the tangent line is positive 40 exactly at x equals negative 2. And therefore, sometimes they just ask for the slope of the tangent line at a certain spot, and you would say it's 40. That's a very steep positive slope at that point. But if they want the equation of the tangent line at that spot, then you're going to use good old y equals mx plus b from algebra. And we just found the m. This is a slope. So we know half the answer already. It's 40x plus something. And then the process, even in algebra, to find b is you plug in an x and a y temporarily so that you can find b. But I don't know the y. All I know is x is negative 2. But if x is negative 2, I could plug that into the original function, not the derivative. The original function, if you plug negative 2 in, that gives you the y coordinate at that spot. So negative 2 to the fourth would be positive 16. Negative 2 squared is 4. 4 times negative 18 is negative 72 plus 81. So 81 minus 72 plus 16 is 25. So this is all happening on the original function at the coordinate -2, 25. They commonly do this where they only give you the x and they make you find the y, but you have to remember to go back to the original function for that, not the derivative. So the y value comes from the original function. The 25 will go right there then, or actually down here. But so 25 equals 40 times -2 plus b. And that's 25 equals -80 plus b. Add 80 to both sides. And because it has such a steep positive slope, it's crossing the y-axis up there really high at 105 actually. So the equation of the tangent line would be y equals 40x plus 105. So first they want the slope of the tangent line, that's 40. That's what the derivative told us. And now they're going to want the equation of the tangent line. And notice they don't have anything yet, so I need to put the y equals, don't forget that, 40x plus 105. Sometimes they already have the y equals there, and then you don't have to do it. And then students sometimes get in the habit, oh, it's always there, I never have to put it, but sometimes you have to put it yourself. You would not have an equation without the y equals. It's easy to forget to write that. Same kind of problem, exactly the same directions. They give me 25 this time, and then they give me some with fractional exponents is the only difference. So, but the procedure is the same thing. First find the derivative, then plug in the given x value so you can get the slope of the tangent line. And then you're going to use that plus the given x to find y and plug it in to find b. 11 x to the 1/2 plus x to the 3/2 at the x spot of 25, and they're intentionally not telling you the y, they want you to find it yourself. Okay, so the derivative, or I could put f prime of x since I'm going to be plugging a 25 in later. So a half of 11 is literally 11/2. It doesn't simplify. And remember when I did 1/2 minus 1 earlier, 1/2 minus 1 is 1/2 minus 2/2, which is -1/2. Where did I have that? It was even earlier than that. It was here. 1/2 minus 1, that was -1/2. So you'll probably remember that one soon because it happens a lot. It's very common to have a 1/2 exponent, and anytime you minus 1, it just goes to -1/2. These other ones you probably will have to do slower if you get like 1/5 or 5/6 or 5/7 or 6/7. But 1/2, it just goes to -1/2. And then here I'm doing 3/2, literally times 1 is 3/2. And 3/2 minus 1 is 3/2 minus 2/2, which is 1/2. So decrease exponent by 1 gets you to 1/2. So they could ask for this. There could be 3 parts instead of 2, and they could say, what's the derivative first? And you would answer this. Then what's the slope of the tangent line at 25? Plug 25 in here to find that out. Now maybe with this -1/2, you want to put that in the bottom because it's going to be hard to do 25 to the -1/2. So I could have rewritten this. See, before I wasn't doing it, but now I would want to, and write this as x to the 1/2 in the bottom. But this one's actually in the top. If it's a negative exponent, it goes to the bottom. If it's positive, it's just in the top. And remember how I said that x over 3 is the same thing as 1/3 x. So when I wrote it like this, 3/2 x to the 1/2, that x is actually part of the top. It's not part of the bottom. This x is part of the top, but because it's a negative exponent, I can move it to the bottom. And then we could even write radicals too. So here's these other versions of it that we normally didn't write them before because it was just wasting time. But now it's actually helpful to write these in some other formats. This is what the best way to write that derivative down as. It's one of the three possible things you could write it as. You could leave negative exponents, you could put them in the bottom, or you could even have radicals. This is the best version to do this, because now you'll see square root of 25 better. Square root of 25. Square root of 25 is easier than 25 to the negative 1/2. It is the same thing, but you might get it wrong. So square root of 25 is 5. This is 11 over 10 plus 15 over 2. So we have to get a common denominator, multiply this by 5 over 5. That way both fractions will be over 10. 11 over 10 plus 75 over 10 is 86 over 10, which both divide by 2, so we should make it 43 over 5, or they'll count it wrong. 43 over 5, that's finally, see, this problem just got messy because of all the fractions. This one was a lot easier here when as soon as I plugged -2 in, I could almost do it all in my head. In fact, I did do all this in my head down here. I didn't use the calculator for that part. But now it got really hard to do all this with a fraction. So 43 over 5, that's the slope of the tangent line. It's a little more than 8.6, but don't put decimals unless they ask for them. Okay, that was weird. I was waiting for the equation of the tangent line. I thought it was the same directions as 7, but they didn't bother to ask that. I guess because it would have been hard to do with a fraction, but you could do it. You could do y equals 43 over 5x plus b. And you would be putting the 25 in for x. And you'd have to plug 25 in here to figure out what y is. And once you got that, that would go here. And actually, this 5 in the bottom would cancel with the 25 and create just a 5 there. So you wouldn't even have a fraction anymore. 5 times 43 is over 200, but it could be done if you had to do it. But luckily they stopped at that point. I guess they realized it was already hard enough to get there, so it was going to get really messy if we kept going. Okay, so we have a cubic function here, 2x cubed plus 39x squared plus 216x plus 12. Find all the values of x where the tangent line is horizontal. That's a very important topic we're going to deal with in the next chapter, actually. F of x equals 2x cubed plus 39x squared plus 216x plus 12. So if I want to know where the tangent line slope is horizontal, that's a derivative again. So 3 times 2 is 6, x to the 3 minus 1, which is 2. I'm doing the power rule 4 different times as I go across this polynomial, and really I'm doing the power rule and the addition rule, but I like to think of it as the power rule 4 different times. 2 times 39 is 78, and then decrease the exponent by 1 to a 1. The derivative of a linear piece is just its constant in front. The derivative of a constant is 0. There's the derivative function. So when you want to know when a function has horizontal tangent lines, think about college algebra when you have a 2x to the third type of graph. This has an odd degree, so the end behavior has the beginning and the ending going in different directions. And then if the positive leading coefficient, that's where you get down on the left and up on the right. That's the end behavior that happens. And this is cubic, so it could have 1, 2 turning points at the most. And it could have 3 x-intercepts at the most. It could have less than that, but this is the maximum it could do. Well, horizontal tangent lines are at these turning points. So there's a horizontal tangent line, and here's a horizontal tangent line. Everywhere else, tangent lines are either positive or negative, everywhere else on the whole curve. So these are special because they happen less often than anything else. And we're going to do more with them in chapter 5 as well. So there could be 2 times that this thing has a horizontal tangent line. Horizontal lines have slopes of 0. So when you're looking for horizontal tangent lines, we already know tangent lines mean derivative. And so you set the derivative equal to 0 if you want horizontal tangent lines. And we do this in algebra where you solve quadratic equations. There can be 2 answers for that. And one thing that might even help here is if I could divide everything by 6, that would help a lot actually. It'll make all the numbers smaller, and it's always best in algebra to have a 1x squared rather than a 6x squared or any other x squared. So let's hope these both divide by 6. Does 78 divide by 6? Yes, it does. 13. And 216 divides by 6 because 6 to the 3rd power is 216. So it's going to turn out to be 36, but you can do it here, 36. Now it's a whole lot easier to factor. We definitely need x times x in the front of each one. When the last sign is positive, you get 2 of these in your answer, so definitely 2 positives. It's a complete waste of time to check anything with a negative in it. I need 2 numbers that multiply to 36. Now maybe you're thinking 6 and 6, but they need to add to 13. 6 plus 6 adds to 12. So then you try another combination, 4 and 9. And then if x plus 4 equals 0, that means x equals negative 4. If x plus 9 equals 0, x equals negative 9. These are the 2 locations where this is happening. My graph isn't accurate, but this is at negative 9, and this is technically at negative 4. So the y-axis, I have the y-axis in the wrong spot. It should be over here somewhere. But when the graph comes up and reaches an x value of negative 9, it has kind of a high point right there. Like riding the roller coaster, you get to the top and now it starts going down. Everybody starts screaming. And so that peak right there, kind of the mountaintop, that's a special spot we're going to study more in chapter 5. And they only occur at horizontal tangent points here. So there were 2 x's. Use a comma to separate your answers, negative 9 and negative 4. That's we're going to deal with a lot more in the next chapter. Same thing here. So we got a cubic function. So again, we can get 2 answers then because the derivative is going to be quadratic anytime the original is cubic. So original function x cubed minus 5x squared minus 9x plus 18. So first I'm going to find the derivative because that's what tangent lines are about. Slopes of tangent lines are derivatives. 3x squared minus 10 x to the first minus 9 plus 0. So if you're searching for the x values that make the tangent lines horizontal, then you can set the derivative equal to 0. These do not all divide by 3, so this is just a harder factoring problem. So the best I can do is 3x times 1x. Now there's a negative in the back, so that automatically there's 1 positive and 1 negative, but because it's 3x and 1x, there's no way to tell which one yet. And then either 3 times 3 or 9 times 1 are my only options for multiplying to 9. And we need to subtract to a negative 10. Okay, so if I could get, and this is the issue, sometimes maybe it doesn't even factor. I was thinking 3 here in the back, because then you'd get 9. And then a 1 here would be a 1. And a 9 and a 1 can make 10, but only if they're both negative, so that didn't really help. Yeah. So what happens sometimes is it won't factor. And then it would take the quadratic formula to solve that. So let me just check real quick that's I don't want to do all that work if it wasn't meant to be that way, but I'm guessing the quadratic formula is going to come out here. Yeah, see, quadratic formula. So usually they give you ones that factor, and this was close enough to factoring, but it missed by a little bit. If they would have made this come out to 8, then it would have worked. Because then I could have negative 3 out here and positive 1 here, and that way you'd get positive 1 and negative 9, and that would make negative 8. So unfortunately, we just have to waste more time and do the good old quadratic formula. A is 3, B is negative 10, C is negative 9. X is equal to the opposite of B. Opposite of negative 10 is positive 10. Plus and minus square root of B squared minus 4AC all over 2A. So negative 10 squared is positive 100. And I always count the negatives here. There's always that negative because that's part of the formula. The 3 and or the 9, they could be positive and or negative. The 9 is negative. So you always get either 1, 2, or 3 negatives in there. And I got 2. 2 negatives is a positive. And then just do 4 times 3 times 9. 108. So x 100 plus 108 is 208. So what I have is 10 plus or minus square root of 208 all over 6. So this is, you just get a decimal answer is basically what's going to happen. The square root of 208 is 14.422205. Round, see how it says, oh no, it does say type an exact answer. That's weird. Okay, I guess they just want it left that way then. So then the other issue is exact answer. We might have to worry about this reducing. So 104, that divides by 2. 52, that divides by 2. 26, that divides by 2. 13. So we can bring out one pair of 2's and a second pair of 2's. That's 2 different 2's, which makes 4. Square root of 13 all over 6. So if you don't do that, they count it wrong. And then all of these outside numbers divide by 2. Then you have to do that too, or they'll count it wrong. So 5 plus and minus 2 square root of 13 over 3. This would be the exact answer. And you can do one with a plus, one with a minus, and separate the commas with separate the answers with a comma. Or sometimes they'll even take it that way. They do have an option for plus or minus, so maybe they would take it that way. But let me just be safe and put 5 fraction. 5 plus 2 square root of 13 over 3. And that's all because they say type an exact answer. Comma 5 minus 2 square root of 13 all over 3. If they said round to so many decimals, then this would have been the method. You would have got a decimal for that and then just added 5, subtracted 5, and divided by 3. But this is very common in calculus. They much prefer exact answers over decimal approximations. So it's a little weird because you probably don't know where those are. But if you're just curious, this is the square root of 208 is 14.4. So if I add 5 and divide by 3, so at about 6.5, that's where there's one horizontal tangent line. If you drew this graph and then got to when x is 6.5 and went up to the graph, there would be a flat horizontal tangent line there. And then if I do, what was that square root of 208 again? 14.42. So if I do 5 minus 14.42 and divide by 3, the other time it's happening is it's a negative 3.1-ish. This was kind of a coincidence that it came out close to what people think of as pi, negative pi. But so roughly negative 3 and positive 6.5, that's where these two things are happening. But they don't like decimal approximations most of the time. So that's why they force us to do it that way. Okay, so we're looking at the ventricular length, as viewed from the front of the heart of a human fetus, has to be at least 18 weeks old, and it's approximated by this function here, L of x, L for length, I guess. So notice we have a polynomial, and it's a quadratic polynomial. They're going to probably have us doing a derivative here in a second. There's parts A through C. So determine a meaningful domain for this function. So two things about that. They did mention at least 18. At least 18 means 18 and higher. So I guess if the fetus is under that, you can't even see the heart, or maybe it hasn't fully developed yet. So 18 is the minimum number. And in theory, it could be 18 to infinity, but fetuses normally don't go past about 9 months. Now this is 18 weeks, so we don't want to have a domain where half of it's in weeks and the other half is in months. So 9 months, and there's roughly 4 weeks in a month, although some months have 5 weeks because it's more like 4.5. So maybe somewhere around 40. They're going with 44, I guess. So just in case somebody doesn't come after 9 months, sometimes it takes a little longer for the fetus to come out. So at least we didn't have to worry about it because they didn't even have a possibility for like 36 or 40. So it should be this one right here. At least 18 means you're starting at 18 and then up to 44, because that's probably about 10 months actually. So just in case, it's a rare case where the baby takes longer. So that would mean all of them would be somewhere between 18 weeks and 44 weeks. Find the derivative. Well, good news is the derivative of a constant is 0. The derivative of a linear piece is its constant in front. So the first two terms are very easy. 0.2418. And then here you just have to do 2 times that constant. 2 times this negative decimal will be negative whatever that equals. 0.001704 times 2 is 003408. And one thing too is if the problem has decimals, that's usually a time where decimals are okay, first of all. And then x, decrease the exponent by 1. So this quadratic is going to drop down to a linear. Whoops, I forgot to put my minus there. Okay, so 0.24. Oh, I guess I had that 0 there for the... Okay. I must have hit 0 instead of minus. I was trying to hit minus, but I must hit 0 instead. So 0.2418, that's the derivative of this linear part, minus 2 times that decimal is this decimal, and then the exponent decreases by 1. So at least that was a pretty easy derivative to do, even though the decimal is really messy. So find and interpret L prime of 25. So I'm plugging in 25. That's the number of weeks of the fetus. Plug in 25 for that. So times 25. That 003408 times 25. And then I'm going to put a negative on it. So that way I have negative that, and then I'll add 0.2418 to it. So 0.1566, and they didn't say anything about rounding anything, so I'll do the whole thing, 1566. The value of L prime of 25 is the estimated blank measured in blank when the fetus is blank. Okay, so you got to come up here and see all this. So L stands for length. Length is the left ventricular. Maybe it stands for left instead of length, but the left ventricular length of the baby's heart when viewed from the front of the heart. I guess if you view it from a side, it's different apparently. Okay, the length is in centimeters, the age is in weeks, so the derivative is the estimated L is left ventricular length of a human fetus, or the rate of that. Definitely not the age and not the remaining growth. Okay, so derivatives are rates though, because that's, remember, slope is average rate of change. So it's not just the L, the length, that's the regular function. The regular function is the length. The derivative length is the rate at which it's increasing because it's a positive answer. So the derivative is always a rate at which the length is increasing. If this had come out negative, they would have said decreasing right there. Length is measured in centimeters. And although it could be centimeters per week, yes, centimeters per week, because a rate is a fraction like that, centimeters per week, when the fetus is 25 weeks old, because the domain was about the weeks of the fetus. Okay, finally, another application of derivatives is, I might have mentioned this in the previous chapter, I don't recall right now, but another application of a derivative is used in physics, velocity. Velocity is the derivative of a position of an object. So they do this all the time in physics. They have S of t. S of t stands for the position of a function at time t. 15t squared minus 9t plus 4. And if you take the derivative of it, s prime of t, that's equal to velocity, how fast the object's moving. And then if you do, later we're going to do the derivative of velocity, and that's another concept called acceleration in physics. But for now, I think they just want velocity. So once you know that velocity is the derivative of position, take your position function, 15t squared minus 9t plus 4, I think it was, yeah. So the derivative of position is velocity. So it's just something we know from physics. Physics uses calculus all the time. So the derivative here is pretty easy. 2 times 15 is 30. Decrease the exponent by 1. The derivative of negative 9t is just negative 9 because that's linear. And the derivative of 4 is nothing. So this is the first answer. My velocity function is 30t minus 9. 30t minus 9. Find the velocity when time is 0. So the time 0 is usually whenever we start keeping track of something. So maybe this is a rocket about to blast off, and then 0 is the blast off moment. So it's easy to plug 0 in right there. And notice it's v of 0 and not s of 0. They could ask for s of 0. And if you put 0 in here, the answer would be 4. So the object is at position 4, whatever that is. But that at the starting time, it's at 4 already. It could be like 4 feet off the ground. And then the velocity at that time is actually negative 9. And negative 9 just means you're moving backwards. So it's like I could drop an object from 4 feet off the ground and it would go -9 downward towards the ground. Say I had a rubber ball and I just let it drop. So I'm holding the ball 4 feet above the ground and I let it go. Its velocity can be -9 because it's going down to the ground. Velocity has direction to it. Speed doesn't, but velocity does. So plug 2 in. 30 times 2 is 60. 60 minus 9 is 51. So it must hit the ground and bounce back up in less than 2 seconds. And by 2 seconds later, it's already going up at 51 units per whatever. It doesn't say what the units here are, but maybe like meters per second or miles per hour if it's like a rocket ship blasting off or something. So that they did this on purpose to show you velocity can be negative or positive. 10 seconds later, the velocity 30 times 10 is 300. 300 minus 9 is 291. So this thing's speeding up fast. This is not just a ball that was dropped. Okay, so that's it. That's 100% on this assignment. We did all 12 problems. Save this. And all 12 of those are done. So we've done, see, rate of change, that's derivative too, rate of change. That's how I knew that one answer had to do with rate. So we got 100, I almost got 100 here, 97.09, and 100 there, and 100 here. So we've done 3 of the 7 sections for this unit. We'll be doing 4.2, 4.3, 4.4, and 4.5 over the next 2 weeks. Review for test 2, all this is due October 21st. Test 2 will appear on October 20th, and you'll have a 2-day window to do it. And I've been slowly adding some more assignments. You'll see some more coming here soon. But we're still like 3 weeks away from even needing to start these. So that's it. This video was just slightly over an hour, so you can see it goes pretty quick when you're doing techniques for finding derivatives. Next will be products and quotients. Remember I said quotients were coming up? And then we do what's called the chain rule, which is functions inside of functions. Derivatives of exponentials and derivatives of logarithms. They have their own rules, actually. So that's it for section 4.1.